Here we're going to learn about maxima and minima. The derivative of a function measures both the slope of the tangent line and the rate of change of the function at any x value, and knowing that the derivative gives you the slope at any instant helps you to find maxima and minima. Because let's think about what a maxima looks like. If something has a maximum, the slope has a certain way that it's changing. It goes from increasing slope to a decreasing slope, from a positive slope to a negative slope. So the slope is the derivative. So if the derivative changed from being positive to negative, we would get a maxima. Here is our maximum, and at that soft peak, the derivative is actually going to be 0. Same thing if we just try to visualize what a minima would look like. So just drawing an example of a minimum, I can draw a parabola. A parabola, the slope change goes from decreasing to increasing. So I go from having a negative derivative, a negative slope tells me decreasing, derivative is slope, to a positive derivative, or a positive slope is increasing, and in between there, that soft peak, the derivative is actually 0. So knowing these sign changes of the derivative gives me a good idea of what the shape of the graph would be, and I'm going to try to find some max and min points in this section. Another way that a graph could look like, it could have an increasing slope, which makes it positive, decreasing is negative. We just saw some of those. We saw the slope is 0 at those soft peaks, but another slope I could just show you guys just to help you visualize this section would be a straight line. That would have a slope of 0, so it would have a derivative of 0 if it was just a flat straight line. Okay, so that's just some sort of intro to tell you what we're going to talk about in this section. Let's actually put in some definitions here. We have a theorem that says, first, if the derivative is bigger than 0, if you have a positive derivative, that means the slope is positive. So if the derivative or the slope is positive, then what was the original function doing? Was it increasing, was it decreasing, or was it constant? It must have been increasing. Positive slope tells us the original function is increasing. So there's another example of increasing, which is this. We just did some parabolas that were increasing. There's a straight line that's increasing. It can look a lot of different ways though. Another option is if you plug into the derivative and you get a negative number out. A negative derivative means slope. A negative slope means that the original function was decreasing. It was falling left to right. There's a falling straight line. The last option is if the slope is 0. Well, we just saw 3 different ways that 0 could look like. It could look like the top of a soft peak would have a derivative of 0, the bottom of a soft peak, or a flat line would have a derivative of 0. So if the derivative is 0, it could be a soft peak, it could be the top of a max or the bottom of a min, or it could just be constant. So a 0 slope is neither increasing or decreasing. It's at the top, bottom of the soft peak, or it's just a straight part of the graph where it's not rising or falling. So there is our concept for this section. For all of these problems in this entire section, we're pretty much doing the same exact 2 steps to determine where something's increasing or decreasing. This is also going to lead into telling us max and min in a little bit here. So whenever we want to find increasing, decreasing, and then later on max and min, we're going to do these 2 steps. And the first step is to take the derivative and set it equal to 0, or figure out where it's discontinuous, make it divide by 0. And then our second step is to test values to determine where it's positive and where it's negative. This second step is called a sign chart. These 2 steps might look like they're intimidating. We're going to do them a whole bunch, and it's not going to be too big of a deal. We're going to do it in this section, and even if you don't pick it up in this section, there are a few sections coming up where we use these same exact 2 steps. So at some point, you're going to be like, okay, I've done this 100 times. We're good. It's not too bad. So we're going to set the derivative equal to 0, or figure out what makes you divide by 0, making that denominator 0, and then we're going to make a sign chart. We want to remember our conclusions from the sign chart. If we plug in and the derivative is positive, then we're going to conclude that the original function f was increasing on that interval. If we plug in and we see the derivative was negative, that means the original function must have been decreasing. saying that theorem all over again because it's super important. I want you to be able to make a sign chart, but then once you make a sign chart and you say, oh, the derivative is positive there, I don't want you to think, ooh, I don't know what it means when the derivative is positive. The derivative is slope, so if the slope is positive, the original function was increasing. The last thing before we hop into some of these examples is that when we set that derivative equal to 0 in the first step, we get a special type of number, and it's called a critical number. A critical number makes f prime 0, or it makes its denominator 0, so it can make it undefined. And we would call it a critical number. So one thing that is important about a critical number, it's in the domain of the function, which means you have to be able to plug it into the original for it to be called a critical number. Have to be able to plug in to the original function f. So let's say you set the derivative equal to 0, and you find that x is -1 makes the derivative undefined. It makes you divide by 0. Well, that's totally fine. It's going to be a critical number as long as it can go into the original function. So even if it makes the derivative undefined by making the denominator 0, as long as it can go into the original function, we'll still call it a critical number. Again, looking at these definitions seems overwhelming and kind of confusing at first, but we're going to do it a whole bunch in these coming examples, and it'll get a little bit better.